Section 5.3 can be considered the heart of the calculus course. It is rightfully titled The Fundamental Theorem of Calculus. It forms a link or a bridge between the two principal branches of calculus, the differential calculus and the integral calculus. And the link is through the process of differentiation in one direction and the inverse or reverse of that process, anti-differentiation. The fundamental theorem of calculus is expressed in two parts. The first part of the fundamental theorem states that an integral function, that is, if we were to define an integral as a function, for instance, of the variable x, that function is an antiderivative, and it is an antiderivative of the function that is being integrated. We call the function that is being integrated the integrand. Okay, and the result of an integral function is going to be an antiderivative of that integrand. Okay, here's how it looks formally stated as in the type notes. If g of x is equal to the integral from a to x of f of t dt, okay, that is where we are defining the integral now as a function of x. So previously we had that the definite integral which had constant bounds, a and b, that would output a number, and that number would be interpreted as the area or the net area bounded by the curve and the x-axis on the closed interval from a to b. Well, if the upper bound is now made to be a variable, the variable x, which notice that the variable in this upper bound here, x, is not the same as the variable in the integrand function. Okay. Well, we'll take a look at this geometrically soon enough, but that is something that is worth noting here. It's important to notice that. Okay, if the upper bound is itself allowed to be a variable, then the output of the integral would actually be a variable function, a function that is dependent on the value of the upper bound. And it's a function that we'll be able to show that if we have, if the integrand, f of t is the integrand here, if f of t is integrable, okay, that is that if it is continuous, if it is sufficiently continuous over the interval from a to x, then the function g of x is going to be also sufficiently continuous and smooth, that it is going to be a differentiable function. G of x would be a differentiable function. And we'll be able to prove that the derivative of g of x would be f of x. And now notice again what the input variables are here. Okay? The integrand is the function, right here is expressed as the function of the variable t. The integral is with respect to that variable t. So t is the input variable of the integrand, and t is therefore ranging from a to x. So x is the upper bound for t. We are integrating with respect to t here in constructing our function, and our function is going to be g of x. If we take the derivative of g of x, we are taking the derivative of it, using the prime notation here, this is a single variable function, the derivative of g with respect to x. Alright, so again, we've integrated with respect to t, but we are differentiating with respect to x. And we'll be able to show, when we build a function like this, g of x function, that it will turn out that g prime of x is equal to f of x. In other words, since another way of stating that the derivative of g is equal to f, another way of stating that is to say that g is an antiderivative of f. So first part of the fundamental theorem of calculus shows that, in fact, an integral is an antiderivative. That is, if we have an integral that is a variable function, that variable function would be an antiderivative of the integrand itself. It's a very important conclusion. We speculated that this might be the case before when we took the velocity function and we did a definite integral of the velocity function. The definite integral on the velocity function output a distance measurement. It was the net change in the position. The net change in the position when we integrated a velocity function is the displacement of an object. So we were able to find the distance it traveled. Displacement is equal to distance if it's only motion in one direction. If it changed direction, then displacement and distance are different than each other. In that case, for distance, we would take absolute values. Okay? But in any case, we said that if we had a velocity function and integrated it in a definite integral, the output of that would give us a measure of distance, and that measure was the displacement. And again, we have that the velocity function is the derivative of position. So the fact that we had the integrand for when it was the velocity function, the integrand was the derivative, right? Was the derivative of the output of the integral in terms of functions, right? Because the velocity is the derivative of a position. And another way to state that is that the output of the integral is the antiderivative of the integrand. For instance, if this was position here, recall that position is the antiderivative of velocity. The fundamental theorem of calculus part 1 proves that this is so for any function that is integrable. And not just the velocity function. And this allows us, therefore, to use antiderivatives in order to interpret integrals. Okay? So previously, we had to interpret integrals geometrically as an area bounded by a curve, and the x-axis, we constructed Riemann sums, which were sums of areas of rectangles. Other geometries could have been used, trapezoids, parabolic regions. You'll take a look at those geometric interpretations for the area under a curve as well in a Calculus 2 course. We use the Riemann sums, the sum of areas of rectangles. But it turns out now that we can conclusively state that we can also calculate a definite integral through the use of an antiderivative function if we can find an antiderivative function. Okay? Not all functions will have an antiderivative. Even if the function can be graphed and we can see that there's an area under that curve, take something like e to the negative x squared. That is a nice smooth and continuous curve, e to the negative x squared. And we can take an area from, let's say, from 0 to 1, and we can draw that area, and we can see that area. But we cannot find the area under e to the negative x squared by the use of an antiderivative. But if we have a function in the integrand that does have an antiderivative, the fundamental theorem of calculus part 1 states that we can use the antiderivative to analyze that function, because the antiderivative would be the output. One application again we have for fundamental theorem of calculus part 1, the derivative and the integral are inverse operators. So that is the differential operator, like the d over dx, okay, is the inverse of the integral operator, using the integral symbol. Okay, and we'll do that here in this section. If we're given a function, an integral function, such as g of x, okay, if we take the derivative of g of x, that would have to be with respect to the variable x. That would equal the derivative of the integral, the derivative of this integral with respect to x, because you would have to take the derivative with respect to the same variable on both sides. And we'll see that the derivative of g, okay, being equal to the derivative of this integral, is going to output a result that is dependent on the chain rule. First, partly dependent on this result here, that we can say if we want the derivative of our g of x right here, the g prime of x can be found by plugging the upper bound x into our integrand function, and we're done. And we'll show that that has to be so. And the extension of that is if the bounds are not just a constant on the bottom and the variable x on the top, if the bounds are instead functions of x themselves, we'll actually have to apply the chain rule in order to take the derivative of an integral. Now, part 2 of the fundamental theorem of calculus tells us how we can use an antiderivative to evaluate a definite integral, which geometrically means we can find the area bounded by a curve in the x-axis over a closed interval a to b through the use of an antiderivative where we would only have to evaluate the antiderivative at the bounds. Okay, so rather than having to evaluate a definite integral by use of a Riemann sum and the limit of a Riemann sum, we could instead use the antiderivative of the integrand, any antiderivative of the integrand. Remember that an antiderivative is a member of a family of antiderivatives by adding an arbitrary constant c, as we saw in a previous section on antiderivatives. If we can find an antiderivative to the integrand, we can plug in the upper bound and the lower bound and subtract those two from each other, and we would actually get the area under the curve. And we'll prove that that's actually so, and then we'll apply it. So first thing, represent geometrically that what this means, that an integral function, first of all, that it exists as a function of x in this form. How does this look geometrically? And that it is in fact differentiable. Okay, let's start by saying let's let g of x equal this integral, the integral from a to x of the function f of t dt, and interpret this integral right here geometrically. So we said previously, all right, that if we had something like the integral from a to b f of x dx, okay, that would be interpreted as, suppose that we have some function, okay, maybe we have some function y equals f of x, and suppose that we have it bounded then from x equals a to, let's say, x equals b. What we mean by this this integral right here is that we have the area of this region right here above the x-axis, and then we have the area of this region that is below the x-axis, and this integral is equal to a1 minus a2, right? It's equal to the area above the x-axis minus the area below the x-axis. And this would just be a number. This is going to output just a number, as long as we have these constant bounds here. So using that same idea there, let's interpret this. Now suppose that we have a function that at the left edge is at where x is equal to a. All right, so let's say we have a curve that maybe it goes up in the positive direction above the x-axis and then below the x-axis, you know, and then maybe back up above the x-axis or something like that. Okay, I'm going to call this the t-axis so that I can represent this integrand function. So if this is the t-axis and this is the y-axis, then what we're looking at here is the function y equals f of t. A is the bound on the left, and let's say we go all the way out here to the right, and I'll call this b out here. So this is where t is equal to b. So if we wanted to talk about what is the integral from a to b, it would be the area a1 minus the area a2 plus this area here a3. All right. If we had the constant bounds a and b. Now let x be an element of the open interval or the closed interval. It could be open, the closed interval. The closed interval from a to b. So that is that x is anywhere from a to b. Right? Then our interpretation for a statement like this, for this integral right here, is that we're talking about how much area or net area is there bounded between the function and the x-axis if we started at a on the left and we went out to x as the right edge. So let's say we go out, you know, let's choose a value of x that's somewhere between a and b. Let's say I choose right here. Let's say that's where x is equal to momentarily, because x is going to be moving. It's going to start at a and it's going to move out towards b. And what happens to the output of the integral as it changes? Well, if x is right here, then for that moment, this is the upper bound then of the integral. And for that moment then, the value of the integral would be this area right here, right, this region. And then if we allow x to increase, right, let's say we allow x to increase to some other value, now maybe x is equal to this quantity right here. Well, then the integral from a to x, okay, would be the net area from a all the way up to this line right here. All right, so then the integral from a to x using this as our x would include all of a1 and it looks like most of a2. So we would have a1 minus this portion of a2 up until x. So we've created a function out of this integral. Right? It increases and it decreases according to how much net area we have dependent on the value of x. Let's take a look at some particular values of x that we could have selected, starting at the left edge. Okay, if x is equal to a, then the function g of a we've defined above would be the integral from a to a of f of t dt. Let's interpret that geometrically. So if we're choosing x is equal to a, right, then a and x are equal to each other, then geometrically we're saying, well, what is the area of this region right here? But that is a region whose width is equal to 0, so there's no rectangle that we could place there that has a width greater than 0. So the actual area of the associated region, when the bounds are equal to each other, that has to equal 0. So g of a is equal to 0. And we can use that then as the first point on our function, the g of x function. Okay, so I'm going to start there. So I'm going to create a grid here where now I'm trying to create a graph of the function g of x. So this can be the y-axis, and this is the x-axis now, right? Up here, this was the t-axis when we're talking about f of t. And now we have the x-axis so that we can graph g of x. Okay? If x is equal to a, this is where a is located, and the output of g at a would just be 0. So this point would exist with coordinates a, 0. So if we're graphing y equals g of x, if we plug a into that, right, the output is 0. Now let's allow the value of x, okay, to increase. So we said what would happen if x was like somewhere like here, we would end up getting a positive integral, right? Let's allow it to go all the way to this point now, right here. What if it went to this point? Let's call that C, and then I'll go out here to this point, I'll call that D. Okay. So what happens if we, so what would it look like if we evaluated g of C now? What is g of C? Well, g of C would be the integral from a to c of f of t dt. That would be interpreted as the area bounded by the function f and the x-axis on the closed interval from a to c. What is that equal to? That would equal this whole area right here. That would be equal to a1. And notice that that is a positive area, an entirely positive area. Also notice, as we choose values of x between a and c, as we allow x to continue to increase in this direction, the associated area under the curve is also increasing. Right? As we increase x, the associated area that we get output from the integral is going to be increasing as well. So by the time we get to where x is equal to c, right, we have what is a positive output to g. That is, that g of c is equal to some positive amount, and that positive amount here is a1. Right? So g of c is equal to a1. Now what happens as we continue past c, right, but don't quite get to d, like we showed already, that if we chose the value of x like right here, then the value of the integral for that value of x would be all of a1 minus a portion of a2 that is going to get subtracted from it. Now I have that a2 looks like it's larger than a1 here, so that might result in like a negative quantity, for instance. Okay, let's choose some values for these. Let's say that I'm going to let a1 equal to 5. Let's say that this is 5 units of area here, or something like that. Let's say that a2 is equal to 7. Notice that a2 is an area, so that's why I'm making it a positive quantity. And let's say that a3, let's make a3 equal to 2. Right? So the area of this is 2. Just as an example, right? They don't have to be, but just as an example. Okay. Now what happens if x is equal to d? That is, what is g of d going to equal? Right? If we choose this as the x value, then the output of the integral, g of d, that would be the integral from a to d. That would be all of a1 minus all of a2. Right? G of d is the integral from a to d, f of t dt. And that's going to output a1 minus a2. Okay? And since I've suggested over here that my area A2 is in fact larger than A1, then that would actually ultimately output a negative quantity for this example. All right, so consider that as x is increasing from C to D, like let's say we freeze it where x is right here. At that moment, then, we would have all of A1 minus this little piece of A2. And the total net area we would have at that x value right there would still be positive, but it would be decreasing. Eventually, we're going to get to a value of x such that the amount of A2 that we're taking subtracted from A1 would ultimately equal 0. They would eventually cancel each other out. And then we're going to continue to increase x towards D, where we're going to continue to subtract more and more area from below the x-axis. So that is that the output of G over this interval is then decreasing, because as x goes from C to D, we are subtracting larger and larger amounts from A1. Okay? But somewhere, maybe around like here or so, maybe around here, is where the area that we would be subtracting from, coming out of A2 maybe exactly equals the area that we had in A1. So by this point right here, right, the output of the integral would be 0, right? Because these areas would be equal in magnitude but opposite in direction. So maybe around here or so, the output of G would in fact equal 0. Okay, and then we continue out towards D. Okay, D is positioned about right here. Okay, and by the time we take the integral from A to D, we should be somewhere negative. That is, G of D is some negative quantity. And if I use these values right here, I have that A1 is equal to 5 and A2 is equal to 7. Then in fact I would expect that right here this value would be negative 2, because it is found by taking A1 minus A2. Right there. Okay. Now let's say we continue out all the way towards B, right? As we choose values of x between D and B, let's choose a value of x like right here. Now we're going to have all of A1 minus all of A2, and then we're also going to add this amount of area. So we're going to move back in the positive direction again. All right, so that means that G is going to start increasing again. And what's going to happen if we let x equal to B? That would be G of B, which is the integral from A to B, f of t dt, and that's going to be A1 minus A2 plus A3. Because we would be taking all of this minus all of this plus all of that, and whatever that equals. And now, given the values I've selected for this example, 5, 7, and 2, that means we have 5 minus 7 plus 2, which, by the way, I've chosen these values here, happens to just equal 0 for this example. Okay? Just as an example. So that I can show that this graph actually comes back, in this case, to like 0. And so it reaches back to 0 by the time we get to where x is equal to b. Okay, so we have the function g, which is an integral function, right? It was a function of x, where x was the upper bound of this integral here. It is changing. It is continuous. We have that g, we can see from the graph there, is continuous, and it is also smooth. That is differentiable. All right, on the interval a to b. It's continuous on the closed interval a to b, but it is smooth on the open interval from a to b. That is, g prime of x would exist, right? G is a function of x, so we can find the derivative of g. Okay. So g prime exists, okay, on the interval, the open interval from a to b, because we had a function that was integrable. All right, we have a variable function. Now, what is the derivative of g of x? Okay. To demonstrate that, we'll go back to the typed notes then over here. All right, so we have a function x, continuous and differentiable. To find the derivative with respect to x, let's use the definition of the derivative. G prime of x, all right, limit as h goes to 0, g of x plus h minus g of x over h. where g of x is the integral function. So let's factor out the 1 over h. What is g of x plus h? Well, that would be the integral from a to x plus h of f of t dt. By the way, g was defined, minus g of x. And of course, this is how g of x was defined. So we have this. Okay. Now we can combine these two. Right? We can combine these two. They both have a left edge at a. Right? So we can consider that the first of those integrals, if this is our f of t function right here, in the example that I draw right here, then the integral from a to x plus h would be the area under that curve from this left bound a all the way out to x plus h out here. That area all the way from a out to here would be representing this g of x plus h. Subtract from that the area from a to x. That would be this area right here. And that would leave us with this area right here. And that expressed as an integral would be the integral of f of t from x to x plus h. And that's this integral right here. So that makes geometric sense, okay, in terms of these areas right here. Now, consider, to find out what this is actually equal to, we see this is the result that we're going to be finding, but how do we prove that that's the result? First, consider the case where h is greater than 0. And if it turned out that h was less than 0, we can make a slight modification here then just to take an absolute value of h instead. Okay, here's what's happening. Okay, let's say that h is greater than 0, so that way x plus h is to the right of x is all we're saying. So it looks like this right here. Notice that what the integral represents, just the integral part from x to x plus h, is this shaded area right here. And that shaded area has bounds. It can be bounded below by us finding a rectangle, right, that is an underestimate to this area, and it is bounded above by us finding a rectangle that is an upper bound to this area. One way we can do that is by keeping the width fixed, x to x plus h, so the width is h, and the height we can choose to be the minimum height of this function along this closed interval. Why are we allowed to do that? Find the minimum? We know that it exists because the function is going to be continuous over a closed interval. See it from the picture. If we have a continuous function on a closed interval, and the extreme value theorem says that an absolute minimum and an absolute maximum must exist within that interval. So we know it exists. We can see on this image right here that the absolute minimum within this interval happens to exist right in here. So let's take that absolute minimum as the representative height of a rectangle throughout this entire region. That's this rectangle right here. Okay? The input, okay, I have the input for that I'm calling u. And so if you evaluate the function f at u, the output of that would be the minimum. Notice geometrically that if that minimum was taken as the height of a rectangle over this entire interval, that area of that rectangle must be an underestimate for the actual area we're trying to find. Right, so the integral from x to x plus h of f of t dt is greater than the area that is calculated as m, which is the height of this rectangle, times h. Right? M times h is therefore a lower bound for the actual integral. Okay, lowercase m times h. Now I'll repeat the process for the absolute maximum. We know that it exists by the extreme value theorem, so we can find the absolute maximum using the closed interval method. We would be able to do that. This is just demonstrating that what we can do with that result. Let's say that we say between x and x plus h, let's say there's a quantity v such that the output from f of v, would be that absolute maximum. We'll call that absolute maximum uppercase m. Well, then the area of the rectangle over this interval with a height of uppercase m, okay, the area of that rectangle must be an upper bound, must be an overestimate to our actual area that the integral is giving us. So an overestimate for our integral would be uppercase m times h. Let's put those bits and pieces together. We have the integral from x to x plus h of f of t dt is greater than or equal to lowercase m times h, where lowercase m is the minimum within that interval, and is less than or equal to uppercase m times h, where uppercase m is the maximum within that interval, right? That has to be true. Now we might note that something that we can do is we can divide all of these quantities then by h in order to get 1 over h, okay? In order to get in the middle 1 over h times our integral. Why is that useful? Because 1 over h times our integral is exactly what we were trying to take the limit of above as h goes to 0. That means on the left we're going to have just lowercase m. On the right we'll have just uppercase m. That would be the output of the function f, so the minimum and the maximum. And in the middle we'll have 1 over h times this integral. Right, so the lower bound is f of u, how we set it up here, and the upper bound is f of v, how we set it up here. So we'll replace the lower bound and upper bound with the function notation for f. Okay, we divide by h, that is, or multiply by 1 over h, and then we take the limit as h goes to 0. As f is a continuous function, as h goes to 0, that's going to push x plus h towards x. Then u and v are getting closer and closer to x. And as u and v get closer to x, the output f of u and f of v get closer to f of x. So the limit as h goes to 0 of f of u is f of x, and the limit as h goes to 0 of f of v is also f of x. And those are both the same. Hence, by the squeeze theorem, the limit of our integral must also be f of x. And that demonstrates what it was that we were trying to show up here, which is that, again, if we take the derivative of our integral function, the derivative with respect to x of our integral function, the output of it would be the function in the integrand with respect to x as its variable. So the derivative of an integral like this, the derivative with respect to x of this integral, where the x is in the upper bound, right? And t is the input variable here. It could be any other variable, but it wouldn't be x in here for this to be true. The derivative of this with respect to x is going to be f of x. That's the fundamental theorem of calculus part 1, stated here symbolically. The derivative of this integral with respect to x, where x is the upper bound, is f of x. So again, that does state conclusively, therefore, that the output of an integral function is an antiderivative of the integrand. Alright, now what can we do with that? Some things that we can do with that. One thing is we can now take the derivative of an integral function. Here's an example. Given that g of x is the integral from 1 to x of the natural log of the quantity 1 plus t squared dt. Okay. Now first I'd like to note we are not able to take the antiderivative of this integral, this integrand. Okay, we are not being asked to actually integrate this in this exercise. The instructions say use the fundamental theorem of calculus to find the derivative of the function. That is, we want the derivative of this integral. So it's important to note that we're taking the derivative of a differentiable function here of x. That means we're taking the derivative with respect to x. It's important to note that x is in the upper bound specifically, and x is not inside of the integrand. The variable of integration is a variable other than x. So when we take the derivative of this, as was demonstrated above, g prime of x is going to be f of x, right? We have the lower bound is 1. We had it stated above that the lower bound was constant, but the upper bound was x, and the function was f of t dt, for instance. Then the derivative of that would just be plug the x into the integrand. That would be the result. Done, right? So that's what we're doing here. Derivative with respect to x of a to x, where a is equal to 1, of some function of t dt. The output of that would be the result of plugging x into the integrand, and we're done. The natural log of 1 plus x squared. That would be the derivative of our integral function. Okay, so now let's take a look at the second part of the fundamental theorem of calculus. The second part states that we can now calculate a definite integral a to b of f of x dx by use of any antiderivative of the integrand f. So we'll call the antiderivative uppercase f, as we did in the previous section on antiderivatives. And we're talking about the general antiderivative. In fact, we can use any particular antiderivative from the set of all possible general antiderivatives. And that antiderivative we can evaluate at the upper bound, evaluate the lower bound, and subtract the difference, or take the difference of the two, and that would be the value of the definite integral. Well, let's prove first that that is actually going to be that is actually true based off of what we now know from part 1. That is that we have, for an integral function, we have that the integral function is the antiderivative of the integrand. So using the integral function g of x, as we had defined already, we can evaluate g at the lower bound, a, and that would just output 0, as we had already seen. And we can evaluate g at b, the constant b, where x is equal to b, and we would get the total area under the curve. And so certainly then the integral from a to b, f of t dt, would be equal to g of b minus g of a, since g of a is equal to 0. Then we can use any antiderivative uppercase f to evaluate b and a. So we get f of b minus f of a is equal to that integral. Now this is not to say that f of a is always equal to 0. We can show plenty of examples where f of a is not specifically equal to 0 all the time, but that this is formulaically how we would be able to calculate the value of a definite integral through the use of an antiderivative. Now we could use any antiderivative, that is the general antiderivative. Recall that we can add any arbitrary constant or any constant we want to an antiderivative, and we would have another antiderivative. Okay, so I'd like to take a look at how we can use part 2 of the fundamental theorem of calculus as another way to demonstrate that part 1 of the fundamental theorem of calculus is actually correct. So g of x is an integral function, and if we take the antiderivative of the integrand f, that is to give us the big F function, evaluated at the upper bound and then the lower bound, that would be big F of x minus big F of a, this difference right here, right? By the second part of the fundamental theorem, this is equal to this integral. Then if we take the derivative of this, right, that was what we were trying to do in part 1, was take the derivative of our integral. The derivative of this with respect to x, well, we would be taking the derivative of an antiderivative. That's going to give us back the original function of x. And then we're going to take the derivative of f of a, but since f of a is a constant, the derivative of that is just 0. So we have that the derivative of our integral, where we found our integral by the part 2 of the fundamental theorem, gave us back f of x. That is the integrand function where we've input the upper bound x. Okay. Now what happens if we switch the bounds? That is, what if in our integral function, what if it was the lower bound that was equal to x? Well, by part 2 of the fundamental theorem then, the output of this integral would be then the antiderivative function f at a minus that antiderivative at x. And then if we took the derivative of that with respect to x, we would get 0 minus little f of x. So what we'd end up getting is we'd get the integral of the integrand evaluated at the lower bound, but it would be negative. So we can demonstrate that that's true by the second part of the fundamental theorem. Now in general then, we can say if we switch the bounds on any integral, on any definite integral where we have bounds, if you switch the bounds, the output of the function is going to be the opposite. So that is easy to show also by part 2 of the fundamental theorem. Okay, right, so FTC part 2, the integral from a to b of f of x dx is big F of b minus big F of a. Okay, now also note then, if we take the integral from b to a, okay, the integral from b to a, that's where I switch the bounds, of f of x dx, that's going to give us big F of a minus big F of b. Okay, and notice that these are exactly opposites of each other. So notice that the integral then from b to a of f of x dx is the opposite of the integral from a to b, f of x dx. Switch the bounds, then you would switch the sign of the integral. Okay. Now let's try using the fundamental theorem of calculus part 2 in an example. Here's a first example right here. Okay. In the previous section, in the notes, we did through the use of a limit of a Riemann sum this integral right here and showed that it was equal to 9. Okay, so we'll take the integral from -1 to 2 of 4 minus x squared dx using part 2 of the fundamental theorem of calculus. That is, first find an antiderivative of the integrand. Recall that the antiderivative of a power function was found by reversing the power rule. You add 1 to the exponent and then divide by the new exponent. So for instance, the antiderivative of 4, that is 4x to the 0, would be 4x to the first divided by 1, or just 4x. The antiderivative of x squared would be x to the third divided by 3. So 4x minus x cubed over 3 plus c is the general antiderivative. Right? The general antiderivative for this integrand. So we can use that, or in fact we can use any member of this family. That is, we can choose any value of c that we want, okay, to use that in the second part of the fundamental theorem of calculus. It's easy to show why that's so. It doesn't matter what value of c we choose. It's because we're going to be subtracting. And since c is a constant, no matter what constant we would choose, f of b is going to have that constant, and f of a is going to have that constant, and then we're going to subtract those from each other. So they're just going to cancel each other out, no matter what constant we would have selected anyway. This is only true if we have a definite integral, by the way. If we're asked the question to just find a general antiderivative, we have to include the plus c as an arbitrary constant. Okay, so we take our antiderivative, 4x minus x cubed over 3, and then here's the notation we use to say that we are now going to be evaluating it at a lower bound and upper bound. So I have x equals -1 at the lower bound, x equals +2 at the upper bound, a and b right there. Plug in the upper bound first, okay, into our antiderivative, and then plug in the lower bound and subtract. Okay. Apply order of operations, evaluate, we get the answer here is 9. Okay, now to complete our introduction to the two parts of the fundamental theorem, we now have everything we need so that we can demonstrate now that this is true. By the chain rule, if we have an integral function where the bounds are functions of x, either one or the other is a function of x, then the derivative of that integral is going to require the use of the chain rule. And we can demonstrate that that is so through the use of the fundamental theorem of calculus part 2. And here I have that proof right here. Find the derivative of this variable function, this variable integral function, where u of x and v of x are both differentiable functions of x at the bounds. Well, by part 2 of the fundamental theorem of calculus, we would take the antiderivative of the integrand, it's big F, and we would evaluate the upper bound at that, so f of v of x, minus the lower bound evaluated, f of u of x. Notice that each of those are compositions of functions now. And if we were to take then the derivative of this, because this is equal to g of x, and we're being asked to find the derivative of g of x, we take the derivative of this output with respect to x, it's going to require the chain rule. The chain rule, so we're going to take the derivative of the outer function. Well, the derivative of big F would just give us back the little f. And of course, with the chain rule, we leave the input alone for the moment. Then we multiply by the derivative of the inner function. Okay, and then we do the same. We do the same for the antiderivative on the lower bound. So the derivative of f of u of x would be little f of u of x times u prime of x. Okay, let's take a look at an example where that would be. Right, where that would be done. Here's one right here. We have the upper bound is a function of x. It's x cubed. Meanwhile, I have the lower bound happens to be a constant here. Okay, and we have that the variable of integration here is theta. Okay, but the variable for the antiderivative function is x, which is found in the upper bound. So what is the derivative of this integral? Well, first, we're going to be able to plug in the upper bound x cubed everywhere where we see the variable into our f of theta function. So that's where we're going to get the sine of x cubed over x cubed. Right, that is actually us finding an antiderivative and then differentiating that antiderivative. That's how we get the sine of x cubed over x cubed. To complete that derivative, we then need to multiply, using the chain rule, multiply by the derivative of that upper bound, and that's where the 3x squared comes from. And the subtracting 0, why that? Because if we took the antiderivative of this function here, whatever that antiderivative might be, and we're not asked to find it here, whatever that antiderivative might be, we evaluate that at pi. The result of that would be a number, just a constant. Then when we differentiate that antiderivative, we're differentiating a constant for that term. And that's why we end up with a 0 there. Okay. All right, let's try another one like that. Using part 1 of the fundamental theorem of calculus, find the derivative of the following function. Okay, so I have h of x, big H of x is equal to the integral from root x to 2x of the arctangent of t dt. Right? Okay, so let's say the lower bound is u of x, right? It is some function of x, and the upper bound is another function of x, for instance. Okay, we want to find the derivative of this function. That is, what is h prime of x? Using Leibniz notation, that is the derivative with respect to x of our integral. Okay, so by the fundamental theorem of calculus part 1, we're going to plug in the upper bound and the lower bound. So we get the arctangent of 2x, okay? And then we multiply by the derivative of that bound, so times 2. And then minus, right, plug in the lower bound. So plugging in the lower bound, we have the arctangent of the square root of x, and then times the derivative of that lower bound with respect to x. That's going to give us 1 over 2 root x. Okay, so cleaning this up a bit, this is how I'd write it. 2 times the arctangent of 2x minus the arctangent of the square root of x over 2 root x. And again, to be clear, what we found is not the integral. We didn't integrate here. We found the derivative of the integral. Okay? We never actually found an antiderivative, but instead we took the derivative of an antiderivative, and we had to take the derivative of the bounds as well, by an application of the chain rule. Okay, let's try an example now using the fundamental theorem part 2. Okay. Fundamental theorem of calculus part 2 in order to evaluate the integral. I have an integral from 1/2 to 1 over root 2 of 4 over the square root of 1 minus x squared dx, using fundamental theorem of calculus part 2. That is that the integral from a to b of f of x dx is equal to big F of b minus big F of a, where f is an antiderivative. Okay, and that's where big F prime of x would be equal to f of x. In other words, that big F is an antiderivative. So we need an antiderivative of this integrand. Okay, recall that this is from our table of antiderivatives. That is, do we know our derivatives really well? Which function has a derivative that looks like this? First, I'm going to factor out the 4 here. You can take out that constant of 1 over root 2, 1/2. Right? The integrand is 1 over root 1 minus x squared. Okay? And we may recall from all of our rules of differentiation in families, okay, that this is the derivative of the arcsine function. The derivative of the arcsine of x is 1 over the square root of 1 minus x squared. Okay? So therefore, arcsine is an antiderivative. Okay? So therefore, this is an antiderivative of 1 over root 1 minus x squared. Now, the general antiderivative of this integrand would be arcsine of x plus c. And we can choose any value of c that we want, and we can use the particular antiderivative. Okay, by that choice in our fundamental theorem of calculus. Okay, so I'm going to choose the one where c is equal to 0. Just take the arc sign. Okay, so so we have 4 has been factored out, and then we evaluate, using the antiderivative, we evaluate at the upper bound, which is 1 over root 2, and then we subtract, and then we evaluate the antiderivative at the lower bound. Recall 1 over root 2, by the way, is the same as root 2 over 2. Okay, so we're saying the sine of theta is equal to root 2 over 2, which happens in quadrant 1. Remember that arc sign only outputs thetas in 1 and 4, quadrants 1 and 4. Okay, and that value of theta that we would get from that would be pi over 4. Okay, so arc sine of 1 over root 2 is pi over 4. Arc sine of 1/2, well, that is if the sine of theta is then equal to 1/2. That also happens in quadrant 1. Okay, that would happen at theta is equal to pi over 6. Okay, so this is pi over 6. Okay, I'll call this one theta 1. I'll call this one theta 2 to distinguish them from each other. Okay, so we have pi over 4 minus pi over 6, and this is times 4. Okay, let's see. So common denominator is 12. So this is what, 3 pi over 12 minus 2 pi over 12. So we get, this is pi over 12, so 4 pi over 12, which reduces to pi over 3. So without having to use a Riemann sum, and without having to use a limit, okay, but by using our knowledge of antiderivatives and the second part of the fundamental theorem of calculus, then, okay, we had to use the first part of the fundamental theorem was to tell us that an antiderivative was appropriate to use, and the second part was that we can plug in the bounds and subtract. Okay, and that gave us a result of pi over 3, which geometrically means that if we were to graph this function, the function y equals 4 over root 1 minus x squared, graph that function and bound it between 1/2 and 1 over root 2 on the left and the right, and bound it below, by the x-axis, the area of that region, okay, would be exactly pi over 3. Okay, let's try another one. Fundamental theorem of calculus, part 2. Okay, let's try to integrate from -2 to -1 the function 1 over x dx. All right, take a look at this real quickly. Geometrically, this is a quick sketch. I have the graph of y equals 1 over x. It looks something like this, right? It has a vertical asymptote at x equals 0, but fortunately we are not trying to evaluate this integral over that vertical asymptote where the function wouldn't be defined. And we do need this function to be continuous within this closed interval, okay, for us to be able to do these integrals right now. We'll take a look in your next semester of calculus. You'll deal with how to integrate around discontinuities through the use of a limit in what are called improper integrals. We want this function for this course, we want this to be continuous throughout this interval, okay, so that we can use the second part of the fundamental theorem of calculus. Okay, that is a crucial part for the second part of the fundamental theorem of calculus, is that the function would need to be sufficiently continuous over the closed interval from a to b. Okay? If it was not, there are things that we could do, possibly, depending on the type of discontinuities and how many of them there happen to be. Okay, but that's for a future course. But we would not do the fundamental theorem of calculus if we were to try to jump over this vertical asymptote, and we're not. So we can take a look at geometrically. The area that we're talking about goes from where like x is equal to -1 to where x is -2. So between -2 and -1. So it's this region right here. Okay. So we have a closed interval. We have a function. Notice we expect this output to give a negative quantity, right? We expect it to be negative. Okay. So let's see if it is. What is the antiderivative for 1 over x? Okay. The antiderivative for that was the natural log of the absolute value of x. Has to be absolute value of x. If we didn't use the absolute value, we would have lost the domain here. This function must exist from -2 to -1, but the antiderivative would not exist at -2 and -1 if we did not use the absolute value. So we're evaluating the natural log of the absolute value of x, okay, from x equals -2 to x equals -1. That's the proper notation to show what we're doing here. All right? Maybe I should have, I really should have shown that up here as well, right? So this is equal to 4 times the arc sine of x, right? Evaluate it from 1/2 to 1 over root 2, which I then plug those bounds in down here. All right, so this is equal to the natural log of the absolute value of -1 minus the natural log of the absolute value of -2. And again, I hope you can see how important it is to put the absolute value there. If that absolute value was not there, if we tried to do the natural log of -1 and the natural log of -2, we would get error messages, all right, from our devices. This is a domain error to try to do this. And that does not mean the integral doesn't exist. Okay, it means that we chose the incorrect antiderivative. So the correct antiderivative for the 1 over x is the natural log of the absolute value of x to avoid those domain issues. So this is equal to the natural log of 1 minus the natural log of 2. Natural log of 1 is equal to 0, and so we have the natural log of 2 minus the natural log of 2. Another way we can write that is as the natural log of 1/2, and that is in fact a negative number. Okay, it certainly is negative, and that quantity represents the net area over this interval. Take the integral from 0 to 1, the quantity x minus t times the square root of t dt. Okay, so why I'm setting this integral up this way. We have two different variables here. We have x and we have t. But the variable of integration is being noted here in the differential, which must be written there. If we didn't write the differential there, we wouldn't know which one of these two was actually the variable. And we talked in a previous section, we looked at why it is geometrically also important to include the differential here. This represents the width of our rectangles. And without it there, we don't have an area. But also, notationally, this tells us what is our variable of interest here. What is the variable that is in motion? So because this is a dt, that means t is the variable, okay? T is the variable of integration. And that means that x is treated as constant in this integral. So we're going to treat x as a constant. Now another interesting thing though about this integral is that we're dealing with a product. So I'll also note, okay, that we are not ready yet to deal with the integral of a product. We have not studied the integral of a product, and that is something for your next course. There is a special rule to taking the integral of a product, much like there was a special rule for taking the derivative of a product. And that is called integration by parts, and that shows up in your next semester of calculus. So instead, because the calculus is going to be too tough the way this is written right now, we should apply some algebra to simplify this. So let's expand it with algebra. So I have x times the square root of t by distributing minus t times the square root of t, okay, dt. That's the integral from 0 to 1. We got what? All right, this is power functions. X t to the 1/2 minus t to the 3/2, and then dt. And now we can find our antiderivative by reversing our general power rule. All right, so if we add 1 to the exponent and then divide by the result, all right, that's how we do an antiderivative. All right, so the integral of x to the n dx is x to the n plus 1 over n plus 1. The antiderivative of it is, okay. In the next section, section 5.4, we'll take a look at the an integral that has no bounds. An integral with no bounds is called an indefinite integral, and what that refers to is that we're going to find the antiderivative, and we're going to add the plus c to find the general antiderivative, right? Okay, so our antiderivative here, let's add 1 to this exponent. 1/2 and 1 is 3/2, and then divide by the result. Well, dividing by 3/2 is the same as multiplying by 2/3. So 2/3 t to the 3/2 power. Minus, now we can Find the antiderivative of t to the 3 halves by adding 1 to the exponent. That would give us 5 halves. And dividing by that new exponent. Well, dividing by 5 halves is the same as multiplying by 2/5. So 2/5 t to the 5 halves. Remember, you can always check your antiderivative by differentiating. For instance, the derivative of 2/5 t to the 5 halves, we would multiply 5 halves times 2/5, which would cancel each other out because they're reciprocals, leaving a 1 as the coefficient. And then we would reduce the exponent by 1 to get us t to the 3 halves. The derivative of our antiderivative would get us back to the original. And we would be taking that derivative of this with respect to t, because we integrated it with respect to t. Okay, now notation for the second part of fundamental theorem of calculus. We have the lower bound is a value of t. It is t is equal to 0, and the upper bound t is equal to 1. Now at the lower bound, where t is equal to 0, both of these terms are going to be 0. And at the upper bound, where t is equal to 1, all right, we'll just be left with what? 2x over 3 minus 2/5. And you can check to see that that's true. 2x over 3 minus 2/5. Okay, and that's what we get from that, right? So we treated x as a constant because the variable of integration was integrated in the differential here. Okay, we did not want to integrate a product of functions of that variable, so we used algebra in order to simplify it. Then we applied the general power rule, fundamental theorem of calculus, part 2, plugged in the upper bound and the lower bound. We also checked our antiderivative, just to be sure, by differentiating to see that we got back the original integrand function. Okay, and we can have confidence then in our answer. Okay, let's bring together the content of 5.2 with 5.3 in the following example. Express the following limit as a definite integral and then evaluate the limit. Evaluate the limit by evaluating the integral. Express the limit as a definite integral. I'll give you that it is over the closed interval from 0 to 1. Okay, and then evaluate. I have this limit. The limit as n goes to infinity, okay, of 1 over n, okay, times root 1 over n plus root 2 over n plus root 3 over n plus ... plus root n over n. Okay. Express this limit as a definite integral. So we'll recall that a definite integral, a to b, f of x dx, is the limit of a Riemann sum. N goes to infinity. The sum I equals 1 to n f of xi star delta x, where we had that delta x was equal to b minus a over n. So we can find out what those bounds are. All right, well, we were already given those bounds right here. Okay, we have 0, we have 1. So we know we're going to have an integral that goes from 0 to 1. Which, by the way, means that our particular delta x would be 1 minus 0 over n. That's equal to 1 over n. And that's exactly what this is right here. All right? So this quantity right here is therefore our delta x. And if we take the limit as n goes to infinity of delta x, we'll recall that that gives us the dx. The limit as n goes to infinity of delta x is what's giving us the differential dx. Okay. Now what about this right here? This is telling us information about the sum. All right, we had delta x is equal to b minus a over n. Well, what about the xi stars? One way we had for finding the xi stars was to use a right endpoint that was like a plus I delta x, which in this case then, if we were using that formula, what would a be? A was equal to 0 plus I, then I is I, and delta x is 1 over n. 0 plus I times 1 over n is I over n. That is a potential formula for our xi stars. I over n. For instance, if I equals 1, we get 1 over n. If I equals 2, 2 over n. I equals 3, 3 over n. And that exactly looks like what we have here. We have the square root of 1 over n, square root of 2 over n, square root of 3 over n. Okay? And we just found that a possible xi star would be I over n, right? Where I is equal to 1, 2, 3, up to n. So what function do we think that we have here for f of x? F of x would be the function of these xi stars, okay, that would output the square root of our xi star. So the function is the square root of x. All right. Written as a Riemann sum, this would be the limit as n goes to, I'll do it down here. Okay, right? This is the limit as n goes to infinity of the sum I equals 1 to n. Okay, our f of xi star is going to be the square root of I over n times delta x, where delta x is equal to 1 over n. Rewriting this in a definite integral form, you could write it like this: the integral from 0 to 1 of the square root of x dx. So we've rewritten it as a definite integral, and now we can evaluate the integral. By evaluating the integral, we would be finding what this limit is going to be equal to as well. Okay, so I'm going to call the integral I. I equals the integral from 0 to 1 root x dx. Okay, I'll write this as a power function, x to the 1/2 dx. Find the antiderivative, fundamental theorem of calculus part 2. Let's add 1 to the exponent. That gives us a 3/2. Then divide by the new exponent. Dividing by 3/2 is the same as multiplying by 2/3. And then plug in the lower bound, x equals 0. Plug in the upper bound. All right, subtract. So starting with the upper bound plugged in, we're going to get 2/3. Okay. Right, so 2/3 times 1 to the 3/2, and then subtract 2/3 times 0 to the 3/2. Well, that's just equal to 2/3 minus 0, which is equal to 2/3. So the value of this limit right here, it is equal to 2/3 by using a definite integral to find it. This step right here is where we applied the fundamental theorem of calculus, part 2. Let's try a sort of differential equation example. Show that the function y equals e to the negative x squared times the integral e to the t squared dt from 1 to x squared. Show that that is a solution to the equation y prime is equal to 2x times the quantity e to the x squared times x squared minus 1, all of that minus y. Okay. Well, let's rewrite our function here. Y equals e to the negative x squared times the integral of e to the t squared dt. Bounds are from 1 to x squared. So I'll note here then that this e to the negative x squared is a function of x. Let's call this f of x. And then note that this integral right here is it is of the form of an integral from a to x, f of t dt, which is also a function of x. All right, let's call it g of x. So what we have here is y is a product of functions of x. It's an f of x times g of x. And we're asked to show that the derivative is this. Well, now we can take the derivative of this by use of the product rule. The product rule, right? So y prime is equal to f prime g plus fg prime. Okay, starting with the derivative of f. Okay? The derivative of e to the negative x squared with respect to x is e to the negative x squared times negative 2x. Right? It's by the chain rule. And then leaving g of x alone, so we have the integral 1 to x squared, okay, e to the t squared dt. Okay, so that's our f prime times g. And then we're going to add to that f times g prime. So f is e to the negative x squared, and now we need the derivative. Get rid of this. Now we need the derivative of our integral function with respect to x. Okay, so we want g prime of x. I'll write here in notation form the d over dx of the integral from 1 to x squared e to the t squared dt. Okay, so we have what? Negative 2x e to the negative x squared, integral 1 to the x squared e to the t squared dt, plus e to the negative x squared, and the derivative of this by the fundamental theorem of calculus part 1, the derivative of this integral here, can be found by plugging the upper bound in to the integrand. Okay, first, that would give us an e to the x to the fourth, right? And then multiplying that by the derivative of the upper bound, which would be 2x. And then we would, subtract, and we would plug in the lower bound, e to the 1 squared, but then we would multiply by the derivative of the lower bound, and that would be 0. So that would just leave us with a 0 right there. Okay? So this right here is by the fundamental theorem of calculus, part 1. Now our goal, now that we've taken the derivative, our goal is to show that that answer is equal to this. That is that we should be able to factor out a 2x, okay, and that we should be left with over here a y, where y is equal to the original product right here. So let's see what happens when we factor out a 2x. Both of these have 2x in it. So I'm going to take out the 2x, and then I'm going to commute the terms. So I take out the 2x from here, I get e to the negative x squared times e to the x to the fourth. Those can combine as e to the x to the fourth minus x squared. It's adding the exponents together, okay? And then minus, we've taken out the 2x here, e to the negative x squared integral 1 to the x squared e to the t squared dt. Okay? Now y was equal to this, e to the negative x squared integral 1 to the x squared e to the t squared dt. And that's this. Right, so that's equal to y. And the other thing for us to do to show that we get the exact answer that we found here, it looks like, is rewrite the exponent in this form. Do we have x squared times the quantity x squared minus 1? That would be x to the fourth minus x squared. And that is exactly what we have here. Okay, so we have 2x. We have e to the x squared times x squared minus 1 as the exponent there, minus this whole quantity here is y. And that's what we wanted to show. Okay, so we had a product of functions, and one of those was an integral function. We needed the derivative of that integral function, and that's where we needed the fundamental theorem of calculus, part 1 of the fundamental theorem of calculus, to do that. So what we have here then is a solution. This is a solution to a differential equation. This is a first order ordinary differential equation which has this integral function as the solution. Okay. All right, so I have one more example to take a look at here which utilizes both parts of the fundamental theorem of calculus. So find a function f and a number a such that the following equation is true. 6 plus the integral from a to x of f of t over t squared dt is equal to 2 root x for all x greater than 0. Okay, well, on the right-hand side, we can see the domain would be that x is greater than or equal to 0. We're saying we want this to be true for all x is greater than 0. Okay. So how can we find a particular function f and then the value of a that would make this equation true? All right, the hint is to use the fundamental theorem of calculus. Okay. Parts 1 and 2. So let's start by using part 1. How would we apply part 1 to this? Well, we have an integral function here. This is an integral function, call it g of x, right? We have an integrand here, which is some function of t, and we have in the upper bound is x. So this is an integral function, a function of x. To take the derivative of that integral function would require part 1 of the fundamental theorem of calculus. To find the derivative of g of x, we need to take its derivative with respect to x. So let's do that. Derivative with respect to x, okay, of 6 plus the integral from a to x of f of t over t squared dt, and that has to be equal to the derivative with respect to x of 2 root x. So on the left-hand side, the derivative of 6 is equal to 0, and the derivative of this, that is going to be by the fundamental theorem of calculus part 1, that we're going to do this derivative right here. And that derivative, okay, of course, if we have a lower bound is constant, the upper bound is just x, then we plug x into the integrand. So that's going to give us f of x over x squared. All right, we plug the upper bound into the entire integrand, okay, which was everywhere where we saw the integral variable t, and the variable of integration. All right, so that's the derivative of the left-hand side. On the right-hand side, we need the derivative of 2 root x. Well, that's 2 times 1 over 2 root x. Okay. So simplifying this, we have f of x over x squared is equal to, the 2's cancel each other out here, 1 over root x. Now we can find our function f, right? We have that f of x, okay, is equal to x squared over root x, which is equal to x, and we can do 2 minus 1/2 for the power here, x to the 3/2. So we found our function f. F of x is equal to x to the 3/2. That was the first part of the exercise, was finding the function f. Now we need to find the number a such that this equation is true. So let's rewrite this equation with our particular function f of x, but we're going to write it as an f of t. Okay, so here, if f of x is equal to x to the 3/2, well then f of t would be t to the 3/2. It's the same function, and if we change the input variable, it doesn't change what the function actually does. So now rewriting the original equation, 6 plus the integral from a to x of f of t over t squared, well, f of t is t to the 3/2, and we're putting that over t squared, and then we have dt, okay? And this has to equal, this is supposed to equal 2 times the square root of x. Okay, and what we're trying to do now is to find a. Well, in order to integrate this, I don't want to find the antiderivative of a quotient, certainly. I would like to simplify this algebraically because we can. All right, so we have the integral from a to x. T to the 3/2 over t to the second is going to give us t to the negative 1/2, or 1 over root t. So I'm going to write it as t to the negative 1/2, and then dt, and that equals 2 root x. Now, in order to do this integral right here, okay, we're not taking the derivative of this integral now. We want the actual the integral itself, and to do that, we're going to have to use the fundamental theorem of calculus part 2, and is to find an antiderivative just to do the integral. We're still leaving the 6 alone, and we're leaving this 2 root x alone as well. But to do this integral, we need now an antiderivative. But the power rule, okay, to find the antiderivative by the power rule, we would add 1 to the exponent. That'll give us a power of 1/2, and then divide by the new exponent. Dividing, so we have a t to the 1/2 divided by 1/2. But dividing by 1/2 is the same as multiplying by positive 2. And then, to complete the part 2 of the fundamental theorem of calculus, the bounds. We are going to evaluate this. The lower bound is t is equal to a, and the upper bound is where t is equal to x. Check the antiderivative here. The derivative of it should be the original integrand. Right, the derivative of this would be 1/2 times 2, cancel, that gives us a 1. Subtract 1 from the exponent, so we get 1t to the negative 1/2, and that is the original integrand. So we found the correct antiderivative. Okay, now evaluating f of b minus f of a. So I have 2 times, we could factor the 2 out of this, or we could leave it in there. Let's leave it in there for the moment. 2 times x to the 1/2, which is 2 times the square root of x, by the way, minus 2 times a to the 1/2, right? And that equals 2 root x. So that is 6 plus 2 root x minus 2 root a is equal to 2 root x. Can we solve this for a? Subtract 2 root x from both sides. Okay, we get 6 minus 2 root a is equal to 0. So 6 is equal to 2 times the square root of a. 3 equals the square root of a. Therefore, a is equal to 9. Yep. Okay. So we have the function f would be would be the f of x equals x to the 3 halves, or you could say f of t equals t to the 3 halves. The function is the function that takes the input and raises it to the 3 halves power. That was the function that would work for this equation. And the correct value of a to make this equation true was that a is equal to 9. In order to find it, we actually applied both to part 1 of the fundamental theorem of calculus and part 2 of the fundamental theorem of calculus. Part 1 was used in order for us to find this as a function. Right? We found it as a function. And then part 2 was used in order to calculate it as an area, to calculate it as a number. Okay? All right. So that is it for the fundamental theorem of calculus. Okay, that it forms a bridge between the differential and the integral branches of calculus. Okay. You'll now be able to use antiderivatives to interpret an integral, okay, as well as in context whatever that antiderivative, by the way, may represent. Such as if the integrand was velocity, we can interpret the integral of that velocity as a change in position, because position, the position function is the antiderivative of velocity. If you had the integral of an acceleration function, right, that integral would tell you information about the change in velocity. Then, okay, the net change in a velocity. So we can use the antiderivative to interpret what an integral is telling us. And we can use an antiderivative to evaluate definite integrals. Okay, for your next section, section 5.4, the only thing really that's new there for us is that you're not going to have bounds on the integral. That's it. You're going to have what's called an indefinite integral. You take the bounds away, there's no a, there's no b, and you call it an indefinite integral. And the result of that is not going to be a number, it's going to be a function. And what function is it going to be when you look at an integral? An integral is going to be an antiderivative. So in your next section, section 5.4, it's back to finding an antiderivative of a function, like we did previously in the course recently. We got some interpretations of graphs there, like we did in the lecture video. All right, using the fundamental theorem of calculus, check the instructions. Sometimes you're being asked to find the derivative of an integral. Okay, take a look at the upper bound. Happens to be a variable, but the variable in the upper bound is different than the variable of integration. That refers to part 1 of the fundamental theorem, where you plug the variable in. And if it is instead a variable function of x, you not only plug that function in from the upper bound in this case, but then you would also have to take the derivative of that upper bound by the chain rule. To do derivative of an integral when you have an integral function of this form. Okay? Evaluating integrals, we now have definite integrals. We have constant bounds, lower and upper bounds. You can use the antiderivative now in order to find what this integral is equal to. That is part 2 of the fundamental theorem of calculus. And you have several examples whereby you do that. Sometimes maybe you'll be looking at a product or a quotient in your integrand. We are not ready to deal with products and quotients as written, so you should apply some algebra to simplify it first. You can take the integral, since we've looked at this before with antiderivatives, you can take an antiderivative term by term. So if it's terms that are separated by addition and subtraction, that would be fine, but not of a product. You don't want to be taking an antiderivative of a product at this stage. Okay? At any stage, if you can avoid taking the antiderivative of a product, it's just better not to. Okay? So evaluate and interpret as a difference of areas, and a couple conceptual questions. Okay? What's wrong with this equation? We did if we take an antiderivative and evaluate it at the upper bound and the lower bound, we get a number. Well, why is that number actually not going to be the correct answer for this particular integral? You can see it's multiple choice here. Okay? See if you can find out what the issue is there, and in this one as well. And let me know if you have any questions. Okay, take care.